Welcome everyone to the first webinar of this series that we are going to have with the Fermentis team in Northern America. So the series will explore the 3 dimensions of beer fermentation, and today we'll start with the first session that is going to be on what we call the first dimension, or the baseline, which is pretty much going to be how choosing a yeast will eventually affect your beer. But I know Kevin will introduce the 3 dimensions a little bit later. Today at Fermentis, we have 3 people with you. My name is Anne Flesch. I am Fermentis Regional Sales Manager for Western North America. And today I will be your moderator, which means I'll get to introduce Kevin and and Brian, and then I will be the one monitoring your questions during the whole chat. If you have a question, please type your question. I'll be checking the question. If it makes sense for me to stop Kevin during his presentation, I will. And if not, I'll keep your question for the end of the presentation. Don't worry, we'll get to it. Then we have Brian Crowder, my colleague in Central North America, who is going to be Kevin's backup speaker in case we have more technical issues today. And then the third and most important person with us today is Kevin Lane. Kevin Lane is our technical sales support manager for the Americas, and today he will be giving the presentation. So it's my honor to introduce him. Kevin has been in the beer and potable alcohol industry for 13 years. He's starting his career working for Breeze Malt and Ingredients company. Then after that, he joined a chemical fermentation company producing food and beverage flavor and aroma products. He then joined in 2009, Miller Coors, where he ran their pilot breweries, both in 40 liters and 10 barrel system. There he was also part for 3 years of their global taste panel. Eventually, in 2013, Kevin joined Fermentis, where he started as technical regional sales manager for the USA and Canada, and eventually moved to his technical support position last year. At Fermentis, I would say that, Kevin, you pretty much work with all different type of segments, the craft and industrial distilling, home, commercial, cider, winemaking, but also home, craft, and industrial brewing industry. Of course, you were part of different you were judged at different international competitions, such as Copa Cerveza de Mexico, and also you were speaker at different conferences just a few weeks ago, for example, at the CCBC Online, but also different MBA chapter meetings, VLB Mexico, Ontario Craft Brewer Conference, Seabrew in Southeast Asia, HomebrewCon, I'm sure I'm forgetting one, a few CCBA. Anyway, speaker at a lot of different conferences. Very happy to have you speak today. I think I'm going to give you the floor now.
Perfect.
And everyone, so we are all going to, Brian and myself, we're going to turn off our camera and microphone, but I'll be monitoring the questions. Is everyone hearing well? I see someone says can't hear because of the music. Is it good for everyone now? Hopefully. Let me know by chat if there is any technical issue.
All right, Anne, thank you for the introduction. As Anne presented me, I'm the Technical Sales Support Manager for the Americas for Fermentis. Today we're going to get right into the first dimension, what we call the baseline of fermentation. I'm going to give a brief kind of background on these dimensions, on what we're talking about, because Dimension 1, the baseline, I think for anybody that hasn't witnessed one of our talks before, may be a little vague, may not give you great direction as to what we're talking about when we talk about these dimensions. And there's a lot of material to cover today. I hope I stay pretty much on time, but we'll find out. And then at the end, I invite Anne and Brian to come back to help me with questions, because I'm sure after these slides, I'll probably need a slight break from talking, and you may need a break from listening to me. So today, what I wanted to do is cover three key areas. The first being the 3D model. And with that, I'll cover what are the three dimensions that we're looking at, what will we look at today, and then we'll get right into yeast characteristics. So this is going to be more what I would consider theoretical, or kind of defining each of these things and explaining how the yeast can produce, or how they can differentiate in these categories. Flocculation, sedimentation's the first. We'll talk about sugar utilization and attenuation. We'll talk about diastaticus immediately following that. Take a look at the fermentation kinetics of the fermentis yeast strains. The alcohol resistance we'll spend a little bit of time on. The yeast flavors and aromas is a huge category. We could devote an entire webinar just to that, and really just to one slide. So we're not going to go too in depth in too much of that, but we'll give you some ideas of how to change those flavors and aroma production, and all that building up to create what we call the Fermentis baseline. I'll explain the experimental protocol, the strain alignment, and how to use that information. So the first thing that I wanted to do today is to really start out and to give you an understanding of what the three-dimensional fermentation model is. But I want to start with a little bit of history, not too long ago, but this is from the MBA Technical Quarterly from 1993, something written by Graham Stewart, talking about what we know about fermentation. And the way that Graham explained beer and the fermentation process, he explained that we know wort preparation fairly well, and we know post-fermentation fairly well. In wort preparation, we know malting, we know mashing, the enzyme activity, the temperatures, the diastatic power of the malts. We know the lautering and mash filtration, temperature of water to use, and your efficiency there. We know about the boiling and the volume loss due to boiling, due to evaporation, and the gravity adjustment there. We know pretty much about protein and polyphenol in the hot and cold true break, what you're losing, what you're removing, what is still remaining. And we know about wort clarification in the whirlpool. Then post-fermentation, we know quite a bit about that as well. We know about processing, aging, and lagering, and what you can expect from that. Blending, filtration, dilution to a certain alcohol, maintaining the same ratio of extract to alcohol. We know about carbonation, different pressures of CO2 at different temperatures, and how that would then relate to either volumes of CO2 or grams per liter, and we know about packaging. And what Graham said in this technical quarterly was that fermentation in 1993 was really a black box. We really didn't know that much about the fermentation phase of making beer. We knew about beforehand the wort preparation, we knew about post-fermentation, but that fermentation part, which involves yeast, which is why I'm talking about it, was more or less a black box. Fast forward to 2016, so 4 years ago, again, the MBA Technical Quarterly, Graham Stewart again, relating back to this paper that he wrote some 20 some years ago before this, and he said again, wort preparation post-fermentation, we know about. Now we can say that fermentation is more or less a gray box. So not really clear, not really well understood, but more understood than it was back in 93 when he wrote that first paper. So that leads me to this gray box. which is the 3D world of fermentation through the eyes of Fermentis. And we're going to talk about these three dimensions in today, and then next week and the following week, taking each one of these axes and investigating it further. So today we're going to be talking about yeast characteristics. The best way that I've found to describe this is the intrinsic character of the yeast, or the inherent character of the yeast. And what I mean by that is when you change from one strain to another, you're not expecting exactly the same profile from one strain to a different strain. For something like lager yeast, you're expecting a crisp, clean, fairly neutral fermentation. From something like a Belgian ale or maybe a Saison type yeast, you're expecting something completely different. So those differences are just the strain differences that you're expecting. Now we know that for all of our yeast strains, they're going to express different characteristics in the fermentation, whether that's sedimentation or flocculation. That's the first point we'll talk about in a minute, or the attenuation, or the speed of fermentation. Any of these things are yeast characteristics that are true to that strain, or at least so we believe. Which leads us into the second dimension, which is the fermentation parameters. So this is where the yeast characteristics are the baseline. Fermentation parameters are things that you can control to maybe alter the yeast and what the yeast is doing in the fermentation process. So these are things like temperature, pitch rate, pH, starting Plato or gravity, any of the conditions that you as a brewer or as a producer can control and change to attempt to influence the yeast characteristics. So that will be next week. I believe Anne will be delivering that presentation. It's really interesting. We're moving through our entire portfolio, doing it strain by strain. Each strain takes a long time to do all this research and then accumulate all the data and then do the statistical analysis on the data. And then the third dimension is the yeast interacting with raw materials. So this being the hops or the malts or maybe the water chemistry. This will be covering primarily or mostly the interaction with hops at this point. We've done some interesting studies within Fermentis on the yeast strains and their interaction with hops, not only on a chemical basis, but also on a flavor profile basis. So how do certain strains interact with hops chemically? And then also the beers went through our taste panel, and there's the expression or the human acknowledgement of those flavors. But today, again, we're going to talk about yeast characteristics. So what we'll talk about today is dimension one. We're going to talk about flocculation, sedimentation, diastatic strains, sugar utilization, attenuation, kinetics, alcohol resistance, yeast flavors and aromas briefly. Again, we could spend an entire webinar doing that. And then we'll conclude at the end with the Fermentis baseline, the Make Your Choice tool, and I'll explain how to use that. So starting with yeast characteristics, this is kind of chapter 2 now. We'll begin with flocculation and sedimentation. So with flocculation and sedimentation, they're not the same thing. I remember 6.5 years ago when I started with Fermentis, I kind of used them as synonyms, talking about the same thing when in fact they are not the same thing. So flocculation itself is the aggregation of yeast cells into a multicellular structure mass, a flock. And that's what these images in the lower right are showing. One flocculent yeast strain where you can see a mass of yeast all together, bunched together, maybe connected in one way or another. And the left image is non-flocculent. So what flocculation means itself is the grouping of more than one cell, usually thousands, maybe millions of cells, and then those sedimenting from the medium under static conditions, mostly because of that size of the mass. The opposite word, so sedimentation, is the act of the yeast dropping out of solution, dropping to the bottom of the tank, which is related to flocculation most of the time, but not necessarily all of the time. In terms of flocculation, there's really a key protein that's on the cellular layer called the flow protein. Here, the image is on the top. You can see the left is inactivated, non-activated flow protein. On the right is activated. It's basically a claw-like structure in this diagram. And it's activated by calcium ions. So the calcium ions are the activating ion for the flow protein. The flow protein, when active, then can meet with the cell mannose, which is the receptor on the outside of the cell. That then forms a bond between more than one cell and forms a flock. In terms of what we say from Fermentis is that a minimum concentration of 100 milligrams per liter of calcium ions is required to allow for good flocculation. And it's difficult because that's what we know. We know that causes good flocculation, but it isn't as easy as saying that you start with X amount. You start with X amount of calcium ions. No, we can't say that because during the mashing, during the brewing process, during fermentation, there's going to be consumption of calcium ions. And that will then affect the residual at the end of fermentation. So for each individual beer, there is kind of a trial and error period for finding what your starting concentration needs to be to end up with the right amount at the end. So it's not as easy as an equation that you can just say, if you start with X, you'll end up with Y. No, it's not true. It depends on your raw materials. It depends on a lot of things in the process in fermentation that then changes the resulting amount of calcium ions in the wort or in the beer at that point. In terms of the two types of yeast, ale yeast and lager yeast, there are some generalizations about the flocculation. Ale yeast tend to be more hydrophobic and less negatively charged. It likely explains the association of flocks with CO2, causing them to rise to the beer surface and be trapped in kind of the foam on top of the liquid. In many modern breweries, ale yeast sink to the bottom of the cylindrical conical vessels, CCVs, your fermenters. And that's due to a number of things, the greater hydrostatic pressure in the fermenters, the modified geometry restricts the CO2 bubble size attached. And then also something that we talk about frequently in Fermentis is the selection process done by humans over the course of history, really. And in terms of the modern strains, the current strains that are available in the market, many of them have been selected over time for the ability to crop off the bottom of the tank. Obviously, if you're collecting from the bottom of the tank, you're only collecting those mutant variants that are falling to the bottom of the tank, not the ones that are stuck in the foam at the top of the tank. So when you repitch, when breweries would collect and harvest and repitch constantly, they were selecting for a certain trait, and that then continued forward. And then when yeast companies like Fermentis or any of the other companies stepped in and started producing these for a larger group of breweries, those were the variants that we had, because that's what was being cropped in the fermenter. Lager yeast, or Pastorianus, really is even more selected, more domesticated over time, because it had a really a recent domestication process, given the revolution of cooling technologies, refrigeration, only being present in the not too distant future. Also, lager yeast tend to be less hydrophobic and sink to the bottom of the tank. We'll revisit kind of the similarities of lager yeast later in this presentation, but because of their more recent evolution or presence in the brewing industry, there is much less diversity, I would say, between lager yeast than there are with ale yeast. Unfortunately, this is a PDF version of this presentation, so I don't have the movement of these things, but here you can see flocculation happening with groups of cells, those then sedimenting to the bottom of the tank. But there is also some interaction with dissolved CO2 in the media. So where standard, typically you'd expect the groups of yeast, the flocks of yeast to sediment because they're larger masses. You'd expect them to sediment out of the solution fast. There are groups of strains that have a higher affinity for dissolved CO2, in which the flocks don't just form flocks and drop out. They'll actually form flocks and then break CO2 out of solution. And in that case, it's not so easy to just say that flocks or flocculation would cause sedimentation, because the yeast is interacting with the dissolved gas in the beer and breaking that out of solution, causing the yeast to rise to the top of the tank and be stuck in the foam. So we'll talk about that coming up here. And that's what we're talking about here. This is an extract from our tips and tricks. The rightmost column is flotation. Flotation is the strain's kind of affinity for the dissolved CO2 or for breaking gas out of solution and probably getting stuck in the foam on top of the tank. But here you can also see the flocculation characteristics and sedimentation characteristics of each strain. There are some strains missing from this. We have come out with new strains recently that aren't included in this data. We'll talk about them a little bit later, not necessarily with each of these specific aspects, but we'll talk about those later. But here, the important thing to see is that you have flocculation, either it's a good flocculator or not a great flocculator. So a plus sign being good flocculation, negative sign being not good at flocculating, or what we call powdery yeast. And then you have the sedimentation characteristics, where even if there's good flocculation, for example, K97, good flocculator, but very slow at sedimenting, also has that flotation characteristic where it's going to break the dissolved CO2 out of solution, float to the top, and get trapped in the foam. Sometimes the yeast follow the rules, like SO4 is good for flocculating, fast at sedimenting, and does not do the flotation deal. But there are some intricacies that aren't necessarily following all the rules. The best example being K97 here. Also, if the opposite, that's true where strains like T58, S33, poor at flocculating, sedimentation is medium, does not do the flotation in the foam. So those strains actually sediment at a reasonable rate, but they're not flocculating with each other. Again, going back to the lager yeast and the limited diversity in lager yeast, you can see they're all good at flocculating, fast at sedimenting, and do not display the flotation characteristic. Here's what I'm talking about with K97. So there are poor flocculators that are red, WB06, T58, S33, that are slow to medium fast at sedimenting. That's the large green arrow going down the screen is the rate of sedimentation. But then there's K97 that's good at flocculating, but very slow at sedimenting. And the reason behind that is that affinity for dissolved CO2, the K97 breaking the dissolved CO2 out of solution, taking that for a ride up to the top of the tank and getting stuck in the foam on top of the fermentation. Again, you see all three lager yeasts behaving very similar to each other, fast sedimenting, good flocculation, and kind of what you would expect from lager yeasts. Here's just a visual image. So the image on the left is a powdery yeast. Powdery yeast. Sorry, I keep saying that too fast. It forms like a powdery blanket across the bottom of the tank, or in this case, it's a bottle. And that is not good at flocculating. So that's sedimenting, but not flocculating. On the right side, top image is flocculating yeast that's sedimented. So you can see it's kind of like flakes of yeast. And then the bottom images on both sides is when you agitate the bottle, what you then see visually from each type of yeast. So the powdery yeast forms more or less like a haze, where the flocculating yeast will form more or less something that looks like snowflakes or flakes of something floating around in the media. And that is a reason for our selection of F2 for bottle and cask conditioning, is that it forms the non-flocculant sediment, which appears nicer than the flaky sediment. So the second topic that we'll talk about in the yeast characteristics is the sugar utilization and attenuation. In terms of the sugar utilization or sequential utilization of sugars, here, let me use the pointer. Okay, hopefully all of you can see my little red dot. So we have these two bottom lines, which are the solid filled in shapes along the line. And those represent glucose and fructose, the glucose being the triangle here, fructose being the squares, very little. And then you have the maltose, the triangle, empty triangle up top, and the maltotriose here. And then the last is the dextrins. So in terms of the fermentation, usually yeast are going to be acting according to this, where at the beginning of fermentation, the yeast are utilizing the simple sugars, the glucose and fructose. You can see that drop. This is theoretical, so it's just, it's not true to form usually, but here you see the sequence. So you can see that the glucose and fructose, the monosaccharides, the DP1s, are being consumed first. Then after those are reduced by a good amount, probably half or more, then the yeast transition into the maltose fermentation, the disaccharide, the DP2. And that you can see here at the 24-hour mark, or whatever this measurement is across the bottom, I think it's hours, when the glucose is reduced by about half, or the fructose by half, you start to see the maltose fermentation coming on much stronger. And then when that fermentation is again dropping by 50%, maybe more, you start to see the maltotriose fermentation, the DP3, starting to be consumed at a faster rate. You can see that the simple sugars are nearly eliminated in fermentation, and then the maltose and maltotriose mostly eliminated, still with some residual sugar at the end of fermentation. Additionally, you can see in this fermentation that the dextrins are not affected. That means that it's not a diastaticus, which we'll talk about briefly in the future. In terms of the difference between yeast strains with residual sugars, each strain is going to present a different residual sugar, residual extract, and then fermentation. This is one of those characteristics of yeast strains. So each strain is going to present something different. Here you can see that some strains have quite a bit of maltotriose, maltotriose being the most important out of the sugars remaining in the beer at the end. Some having over 10 gram per liter, some having less than 5 gram per liter, and then there's 4 that have zero residual maltotriose. Those being B256, WB06, B134, and HA18, each for a different reason. So B256 is our highest attenuating yeast strain that is not diastaticus. So that's not going to touch the dextrins, but it does ferment all of the maltotriose. WB06 and B134 being diastaticus strains, WB06 being a little bit less aggressive, B134 more aggressive, and then HA18 is a fermentation solution. We released it, I want to say 2 or 3 years ago, which is a blend of enzyme and yeast, special yeast selected for the high osmotic pressure, high attenuation, that strain really achieving really high alcohol if you give it enough sugar at the beginning of fermentation, really ferments out everything. Again, going back to the similarities between lager yeast, our three lager yeasts don't display that much difference, where you see the ale yeast ranging from 0 residual maltodextrin up to 11, 12 grams per liter. The lager yeasts all having 2 or 4. Again, there isn't that much diversity. They are different, of course, but they're not as extreme as the ales are in terms of differences. When you look at the residual sugars DP1 through DP7, here DP1 and 2 are grouped together, the glucose, and that should be fructose, not maltose. Or sorry, DP1, 2, sorry. Glucose, fructose, and maltose. DP3 maltotriose, DP4, and DP4 through DP7 being the dextrins. Here you are seeing significant differences between the ale yeasts again. Over on the left, the first 3 strains are the 3 lager strains, S23, W3470, and S189 are all SAF lager. And then the rest are the ale strains. And you can really see a significant difference between the ale strains in terms of the residual sugars at the end of fermentation. Here we are lacking a few strains. This chart was put together before we released B134 and H18 and a few others that we'll talk about in the coming slides. Maybe, I don't know, 20 slides from now, but we'll talk about others. But really, you can see big differences in the DP1 and 2 and the DP3, or in terms of the WB06, you can see a big difference in the dextrins compared to any of the other yeast strains, being because WB06 is the only diastatic yeast strain in this group of yeasts. Here, this apparent attenuation, which will be related, of course, to the residual sugar. In this study, we did have B134 included in this study, so you do see it there. And here you can also see the difference between an aggressive diastaticus, B134, and a not so aggressive diastaticus, WB06. WB06 being here at about 86% attenuation, B134 being well over 90, somewhere probably in the 89 to 95% attenuation range. And then you can also see really low attenuating strains like S33 having roughly 70% of attenuation. What I always like to point out when looking at this apparent attenuation, these kind of graphical analysis, is the way that these are produced is in a very limited set of fermentations, all targeting just having the same base wort, the same fermentation capability. And it's a way for you to compare 2 different strains in the same media. The reason I say that is because there are many things you can do during the brewing process or in your ingredient selection that can alter the attenuation. The attenuation isn't some magical number that this yeast is always going to achieve, because as soon as you introduce simple sugars, if you were to add dextrose to your beer, the attenuation of all the strains is going to increase in the same media. Likewise, if you use more dextrin malt, the attenuation would decrease because of that complexity of dextrins that you're adding to the wort. Likewise, if you were to use enzymes, exogenous enzymes, you could alter the fermentable potential of the wort and change the attenuation completely. So I say all of that just to remind you that attenuation is just for making a selection between 1 or 2 or a few strains in the same media. So you could say, in general, B134 is going to be a much drier, a much less sweet beer than S33, which is going to have more residual maltotriose, more residual sugars, and thus have more fullness on the palate, more sweetness maybe, because of the residual maltotriose. All of that leading into diastaticus. So this was the hot topic. I remember 2 or 3, maybe closer to 4 years ago, 3 or 4 years ago. Saccharomyces cerevisiae variety diastaticus. first isolated in 1952 for its ability to reduce starch and dextrin to fermentable sugar. I think the oldest paper that I found on Diastaticus when I was looking into it 4 years ago or whenever that was a paper from Guinness, and I think it was sometime in the 1940s. So it's been known about for quite a long time. That paper that I found was talking about attempting to name the Diastaticus strains as a new species, which obviously didn't take because it's a variety of Cerevisiae. But it's been known about for a long time. Really, what the variety Diastaticus means is that it has the capability of producing extracellular glucoamylase or amyloglucosidase, which cleaves the bonds of alpha-1,4 and alpha-1,6 bonds in the amylose or amylopectin, or the dextrins, breaking those down to simple sugars, which are then fermentable by either the Diastaticus strain or by any other strain that's around, because all of the yeast will ferment glucose and smaller carbohydrates. So that's really the definition of Diastaticus. It's the ability to produce the extracellular glucoamylase. What's interesting is that there are SGA genes, which express a sporulation-specific glucoamylase, which enables the use of glycogen during sporulation, which all Saccharomyces cerevisiae have. The variety Diastaticus seems to have the STA genes or something similar, which seems to be a genetic recombination of the ancestral SGA genes, which then give this yeast the capability of producing extracellular glucoamylase, which with this image in the upper right, you can see the alpha-1,4 and alpha-1,6 bonds, which gives the capability of those breaking and then thus forming smaller carbohydrates that are fermentable by yeast. Some can even remain active after yeast separation, which means that it's just kind of floating around in the media. When it comes to the strains that have this Diastaticus trait, many of the wild yeast strains are Diastaticus. So if you are one of those brewers that goes out and tries to collect yeast from sap or from a flower or from fruit or whatever you're using, I've heard of bark being a really great source of yeast. Most likely you're going to catch some Diastaticus yeast. But there are also some commercial examples like SatSour WB06, SatSour LP 134 that we've selected as fermentis to bring to the market, which are in fact Diastaticus. In general, they're Belgian strains, not always. Obviously, with WB06, it's more of like a wheat beer strain, Hefeweizen or wheat beer type strain. Typically, the Diastaticus are POF positive and highly attenuating strains. Now, the potential impacts of Diastaticus is that it gives some risk to post-packaging re-fermentation, which can lead to bottle bombs or can bombs, over pressurizing the container, which poses a safety issue not only for the end consumer that's buying your beer and taking it home, but also for anybody in your brewery. If you have bottles of beer or cans of beer around somewhere that are at ambient temperature, most likely the Diastaticus could continue to ferment if it is not done already. So remember, I said that there are commercial examples. As long as you give those commercial examples the appropriate time to ferment, you won't have problems in the packaging or over attenuation or any of those things, as long as you give it time to do what it's going to do. The other potential impacts are over attenuation, so a drier finished beer, less body to it, phenolic off flavor because most of the Diastaticus strains are POF positive, and a potential violation of whatever the regulations are. In the US, it's TTB, but in other countries, I'm sure there's similar guidelines where you have some cushion for being off on your alcohol, But if you have diastaticus contamination and it continues to ferment in the package or beyond what you think, then you'll have a higher alcohol concentration in the package than what you say is in there, and that can be a legal issue. I'm taking way too long on this material, so I'll try to continue to move faster than before. Not all the STA positive yeast strains express the diastatic characteristics. Some strains possess genes that can suppress that expression of the STA genes. The activity between different STA positive strains can be much different. Examples are B134 and WB06 having different attenuations, even though they're both diastaticus. And other factors such as carbon and nitrogen sources can affect the expression of the STA genes. Moving on to the fermentation kinetics. This, I think, is a great tool for most brewers, as long as you are really looking at it and understanding what you're looking at. Within Fermentis, we set up experiments to produce this information to give you an idea of what you should expect from the different yeasts. These were done in EBC columns. The original gravities were 13.5 and 18 Plato of malt extract for the yeast, and then original gravities of 25 and 30 degrees Plato for malt extract for the fermentation solutions, which we now have 2 of. Only one of them is covered in this. And then the temperature for the lagers was 12 degrees C for 48 hours, then risen to 14 degrees C until the end of fermentation. For the ales, for all of them except for one of the ale strains, we did 20 degrees C until end of fermentation. There is one that we changed the temperature with just to see the impact in this study. And then for the fermentation solutions, it was 25 and 35 degrees C. This information is also included in the tips and tricks. I think it's really, there's a lot of information that's given here. You just have to know how to read it, know what you're looking at. Sorry for that, just needed a sip of water. So here's the 13.5 Plato, 20 degrees C for our ale strains. And you can see there's quite a bit of difference between the strains here. Again, that's what we're talking about today. The first dimension is the differences between the yeast strains themselves in the same media, that we're keeping the media consistent, the same, and you're having different expression by the different strains. One thing I like to point out here is that strains in a 13.5 Plato, the strains USO5 and K97 have roughly a 1-day lag phase. We'll see again, USO5 in the 18 Plato has lag phase. So those are the 2 here down at the bottom that have roughly a day lag phase and then start to ferment. We have a lot of strains, most of the strains that take off right away, some that are much more aggressive, very fast growth and implementation and fermentation. Some like WB06, which is the gray line here, which takes quite a while, over 10 days to ferment a 13.5 Plato. Same with USO5, which is this dashed kind of purple, dark purple line. And then there's some strains that are in between. So in these kinetic graphs, you can see the lag phase, you can see the growth, the speed of fermentation, you can see the attenuation level, where the strain reaches and where it maxes out, and you can see the differences for what you would expect in the resulting beers. A lot of information in one graph. Here again, you can see that the USO5, that dashed darker purple kind of line, has about a 1-day lag phase. The rest in this study at 18 Plato started right away. We're fermenting by the 24-hour period. But again, you can see differences in the rate of fermentation, in the time that it took to complete fermentation, in the attenuation level reached by each of these strains. So there's a lot of information in fermentation kinetic graphs. We're not going to go through each strain individually, but this is something that you can look at in the tips and tricks to see, where you could expect one of these strains to be in a related media, meaning a similar starting Plato with 20 degrees C. One thing that I think is important to point out, because USO5 is very popular, is that the time that it takes to ferment out is strongly dependent on the starting gravity. So here you have the percentage of the sugars that USO5 will ferment, so 0 starting at the beginning of fermentation up to 100% when the fermentation has been completed by USO5. It doesn't mean 100% attenuated. It means 100% of the sugar that USO5 will ferment. And what you see here is that at 13.5 Plato, you have roughly, 12 days, let's say. When you move up to 18 Plato, you're going to be at about 16, 17 days. If you decide to make a 22.5 Plato wort fermented with USO5, it can take up to 25, 26 days. Those are very different and express the fact that when you change one of the parameters, which is what Anne will talk about next week, when you change one of the parameters, the fermentation will be different. Moving on, here's where we have the different fermentation temperatures with the ale yeast. So you have 20 degrees C, 25, 30 for BE134, and then WB06 at 25 degrees C, just as a kind of relatable strain. Here, again, you can see that if there is or is not a lag phase, here clearly there's not. How that temperature may slightly affect the rate of fermentation, this orange line being at 20 degrees C at a standard ale temperature, 30 degrees C being this very faint line, the fastest out of all of them. Also, you can see WB06 compared to BE134. WB06 is the lowest attenuation out of all 4 of those, that being because BE134 is slightly more aggressive. Other highly hyper-attenuating yeast, which is actually a fermentation solution, is HA18. These fermentations at 25 and 30 degrees C. Also, these are 25 and 30 Plato. If you take a look at these, this fermentation product is a monster. It's fermenting out a 30 or a 25 Plato wort in somewhere between 3 and 6 days, reaching nearly 100% attenuation for the 30 Plato, for sure reaching 100% attenuation for the 25 Plato. It is a monster. It's very fast. It produces a lot of alcohol, can tolerate that, and can tolerate the very high gravities. This is a new member of the Fermentis portfolio, DA16. I don't have that much information here on this strain. I just wanted to show, again, this is a fermentation solution. And again, this is going to be 20, 25, and 30 Plato worts fermented to completion in, 5, 6, 7 days. Again, very fast, very, very high attenuating for those specific gravities or those Platos. Going back to the standard range, the SAF lager range, again, 13.5 and 18 Plato. Again, I go back to the fact that the lager yeasts in general are not going to be as significantly different as the ales will be from each other. So here you're not seeing big differences between the lag or the slow beginning, the rate, the fast growth rate, the rate of fermentation, and the attenuation. They're all very similar. There are differences between the strains, of course, but they're not as extremely different as the ale yeasts are. Here again at 18 Plato, again, remember this is 12C for 48 hours and then 14 until the end of fermentation. With 18 Plato, it does take over 2 weeks to achieve the end of fermentation. Going back to those apparent degree of fermentation, you can see the percentages listed here. Again, this is an extract from the tips and tricks, something that I hope all of you are familiar with, or one of the sales people or distributors can get you a copy of it. It's got a lot of information in it, a lot of great information. Good thing to read if you have some time. But here you can see a strain like S33 has a apparent degree of fermentation or attenuation of 68 to 72%. whereas B134, a diastaticus strain, has 89 to 93%. Again, the lager yeasts are all going to be very similar to each other because of the lack of genetic diversity. Going on to alcohol resistance. So this is, again, an extract from the tips and tricks. It has been updated since this image with more or less an alcohol tolerance as well. So the alcohol resistance is when you put these strains into a very high gravity solution, what alcohol will it produce? I don't remember specifically the starting Plato of these fermentations, but here you can see, most of the ale strains are going to be somewhere between 9 and 11%. With the new information, the alcohol tolerance, I believe, is up to 15 for most of the strains. And the reason for that difference is if you control the conditions better for the yeast, they'll be able to achieve a higher alcohol solution in the end. So this is alcohol resistance, not alcohol tolerance. That's going to be much different. Again, the lager yeast, you're not seeing very much difference between them. They're all fairly similar. I can't speak from my own experiences and say that with, I think, US05 and 3470, I was able to make 12.5% beers with those, even though this resistance is at 9.25 or 9.3 and 10.5 for the lager. Here's what you're seeing. So remember that study was done on very high gravity. Here, what you see is that with the yeast, they will reach a maximum alcohol produced, depending on the original gravity. And then as you continue to increase the starting gravity, you'll have a decrease in the amount of alcohol produced because of the complexity of the media and the other stress factors that are affecting the yeast. So this previous image was saying here, whereas you can achieve a higher alcohol with a reduced starting gravity. One of the new products, excuse me, that wasn't included in all that data is a yeast strain that we came out with in the past year for LA and NA, so low alcohol and non-alcoholic beer. And that strain is SAF Ale, now SAF Brew LA01. It's a Saccharomyces cerevisiae variety Chevalieri. It is maltose negative, so it's only going to ferment the simple sugar, the glucose fructose, which gives you an apparent degree of fermentation of 10 to 15%. Not very much when you compare that to the rest of the yeasts, which are going to be 70, 80s, 90s, up to 100. This strain does produce the aromatic characteristics of beer. So we'll take a look at that briefly in a couple of slides. It is POF positive, but because you have such a limited amount of fermentation, the 10 to 15%, you don't have that strong of an expression of POF, of phenolic character, which we will talk about later as well. Here are the fermentation kinetics at different starting gravities, so 6, 8, 10, and 15 Plato. You can see that the limit of fermentation is reached in 60 to 75 hours, depending on the gravity. Here you can see that if you're somewhere around 7 to 8 Plato, you're going to hit that 0.5% alcohol by volume mark, which is the non-alcoholic beer marker in many countries, for sure in the US. But also producing low alcohol beer if you go beyond that. Not the intention of this strain, but you can do that, of course. Here's where we're talking about the aromatic complexity. So you can see the acetaldehyde, isoamyl alcohol, isobutanol, diacetyl was below threshold. Even if these different flavor compounds, aromatic compounds aren't at threshold, it still gives the complexity of flavor that you would expect in a beer. So even if you're not at threshold level, not that you wouldn't be able to necessarily detect and say that's for sure isoamyl alcohol or that's for sure isobutanol. Because it's present and because it has a reasonable ratio with the other compounds, it's going to present the flavor that you're expecting from a beer. Additionally, we came out with a bacteria in the past year called SatSour LP 652, intended for kettle souring. I apologize for some typos on this slide. I made some mistakes. I saw this earlier. But selection by Fermentis, it's ideal for sour beer production. Typically produces notes of citrus, fruity, and a fresh sensation. It's homofermentative lactic acid bacteria, meaning that it primarily produces lactic acid in that souring fermentation. What I found interesting about this bacteria is that it has a lower ideal temperature than what I previously thought. But with this specific strain of bacteria, it really ideally would like to be in the 30s or 30s up to 40 degrees C for the appropriate souring. So it is easy to use, which means that we can go through that at a different time so I can keep pace with this time that I have. The pitch rate is 10 grams per hectoliter. The lactic acid fermentation is 24 to 36 hours, temperature range of 30 to 40 C, expecting a pH of 3.2 to 3.6. So it's a highly reliable bacterium to produce balanced sour beers. Now we're getting to the really complex part of yeast flavors and aromas, and I apologize because now I have even less time than I thought I was going to when I got to this part of the presentation. But here, this is a diagram that we use internally in Fermentis. I'm not going to go through this extensively. Again, I think we could spend an entire webinar going through this diagram itself. What I wanted to show with this is that you have some inputs into the yeast that can then create a lot of different products in the end. So here, if I use the little highlighter again, we have the sugars going into the yeast cell and then going through the glycolysis pathway. But then from there, it can be split off in a number of different ways, producing a number of different outputs from the yeast. Some of these pathways that are split, that have a fork in the pathway where there's two options or more, can be controlled. And we're going to go through that in the next few slides, how to maybe favor certain production or limit certain production. But the important thing to look at is the outputs of the yeast. And there you have glycerol, acetaldehyde, acetic acid, ethanol, of course, CO2, heat, ethyl acetate, ethyl esters, fatty acids, acetate esters, higher alcohols, diacetyl, H2S, sulfites. There's a lot of different things that the yeast are producing just from the sugar fermentation or taking in sulfur compounds, converting them for the production of amino acids, or taking in amino acids and converting them to higher alcohols or whatever. We're going to go through it briefly in the next few slides, but I don't want to take up the entire 2 hours with this. So we'll move through this material pretty quickly. Maybe if there's encouragement from the audience, we could have a webinar on this in the future. I'll leave that up to you guys. So in terms of the flavors and aromas, there's ethanol and CO2, which don't impart that strong of a flavor or aroma necessarily. Ethanol does increase the warming effect in the mouth. It does reduce the vapor pressure, assisting with the evolution of other aromas, similar to the CO2. The reason that you serve beer carbonated usually is to carry the aromas and flavors out of the beer so you smell and taste them. There are volatile compounds, acetic acid and glycerol, which are not volatile compounds, but they're included in this slide. Organic acids, fatty acids, flavors derived from nitrogen metabolism, esters, higher alcohols, aldehydes, sulfur compounds, and phenols, all volatile compounds that you can appreciate or maybe not appreciate if they're in the wrong media. So we'll go through how a lot of these are produced, but we're not going to go in depth because I'm already at the time marker of 65 minutes, and I still have a number of slides to go through. So the TCA-related organic acids in beer primarily associated with suppressed TCA cycle. They add sourness to the beer, some acidity. You can see the typical concentrations Also, some can add like a salty bitterness flavor to the beer, but really, it's true for a lot of the volatile compounds, or a lot of the compounds that yeast are producing in fermentation, that if the yeast are stopped or if they overproduce something, they need to create some balance, or they need to remove it from the cell so that it's not overpowering the cell. So a lot of these would be intermediates in the TCA cycle, and if it's suppressed, or if there's a stoppage for some reason, or an overproduction of some of them, the yeast will release it into the media. Yeast are not a perfect machine. They are a great machine. We like them a lot, but they're not perfect. So with a lot of these flavors, a lot of these aromas, it's going to be an excretion, because it's not a perfect mathematical, linear equation. Fatty acids yeast can build them internally. For unsaturated fatty acids and sterols, and intake it from the wort, it's important for the yeast membrane, for fluidity, to have the unsaturated fatty acids, which when you use Fermentis' yeast from the dry form, it's something that we know that there's zero oxygen demand for the first fermentation, because the yeast already have enough unsaturated fatty acid and sterol present in the membrane to undergo multiple multiplications. So I challenge most brewers, when I talk to them that don't believe me, to just try it once without oxygenating your wort, run the fermentation, and at that point send me an email if you find a difference. And I never receive those emails, so I think it works pretty much every time. I've never received an email that said that anybody was upset about it. They're usually excited that they didn't have to do that. For the fatty acids, these lipids can be cell growth limiting factors, which is usually why you would oxygenate your wort. Larger fatty acids assimilate into structural lipids for the cell membrane. Shorter chain fatty acids, C8 to C14, released and toxic to yeast, surfactant effect, can be esterified to avoid toxicity, and fatty acids are associated with unfavorable aromas in beer. Moving to higher alcohols, mostly nitrogen-related metabolism, the creation of keto acid pool through either the anabolic or catabolic processes. Here you can see the amino acid to keto acid, then decarboxylated to phenylaldehyde, and then converted to higher alcohol. So that's the process that the yeast is undergoing, producing the higher alcohols. It's related to the lipid metabolism, normally associated with the end of the lipid synthesis, and sometimes not a negative thing, sometimes a positive thing, but as we saw in that overall view of the cell and the creation of different flavor compounds, the higher alcohols can be used to create some esters. So it's important for some ester production to have those higher alcohols present. To increase the concentration, ferment at higher temperatures. It's the most important parameter. Increase the yeast growth, primarily high rates of oxygenation, true lipid or agitation as well, and also low and high levels of FAN. The low requires a high need of anabolic pathway, the high excessive keto acid production inside of the cell. And then again, like I was saying, with yeast not being a perfect organism, it overproduces the keto acids and then has to do something with it. So produces the higher alcohols. Esters, again, this is really the basic overview of the two categories of esters produced, the ethyl esters of fatty acids and the acetate esters coming from the higher alcohols. Here, you can see higher alcohol is an intermediate step in the path. So from amino acid ingress to higher alcohol with acetyl-CoA, then producing the acetate esters. The ethyl esters really coming more from the glycolysis pathway, but both of the esters producing, the ester flavor profile being fruity, banana, apple, perfume, sometimes solventy or nail polish remover for some of the more negative esters. When we did the studies on the residual sugar and attenuation, we also did the ester levels of the different yeast strains. And this was kind of a basis for going into this first dimension of fermentation that we wanted to investigate more, where you see the ester levels of each strain. Sorry, here. So again, we have the 3 lagers grouped together again because they're not too dissimilar from each other. They're creating really a crisp, clean fermentation. Then we have the start of the ales with USO5 having the least amount of esters, SO4, K97 becoming more estery. And then you see really a big difference between, for example, USO5 and B256 or T58 or WB06, where you have close to 6 odor units, so 6 times the threshold of isoamyl acetate, the banana character in beer, for those 2 strains, or, there's differences in the ethyl acetate, ethyl hex, for each strain as well. In terms of controlling the esters, really can come down to a number of different things. One of the ways to do it is to make acetyl-CoA more available so that it can increase the esters. To do that, lower the aeration, less sterol and fatty acid biosynthesis allows for more acetyl-CoA to be available towards the ester production. Increase the pitching rates, which causes less yeast growth, again, allows for more acetyl-CoA. Lower fan, because the acetyl-CoA is tied up in nitrogen metabolism. So those are ways to increase the acetyl-CoA for ester production. Higher temperatures can increase ester production, and true birch wort can lead to more sterol formation and therefore lower ester production. Sulfurs, really, you have some sulfates coming in here or sulfite coming in, and the yeast is using that for amino acid production, for protein production. You can also have amino acids or ammonium coming into the cell and then entering into the process for the sulfur amino acids, but yeast will also convert the sulfates to sulfites and release those, or sulfates to sulfide, or sulfite to sulfide and release that. So the 2 most important sulfur compounds that are negatives in beer would be SO2 and H2S, giving the sulfur characters that you should be familiar with, struck match and egginess. To control the compounds, the sulfur compounds, with yeast growth, the uptake of H2S into amino acids is significant, keeping excess under control. You can do that with more oxygenation or healthy yeast. That's key. Having healthy yeast reduces the amount of sulfur production. H2S and SO2, the 2 negative ones, most usually associated with sulfur, can easily be scrubbed from the liquid by CO2, potentially by fermentation temperature. If there's a heavy enough fermentation happening, it can really push the sulfurs out of the tank. Lack of sufficient cofactors and vitamins may produce noticeable levels of H2S or SO2, and top pressure can increase those sulfurs. Another one of the negative flavor compounds, excuse me, vinyl diketones, VDKs, are produced by the yeast in the growth phase when they're producing isoleucine and valine. It's an intermediate of those productions, causing the release of these 2 compounds here, then being converted to 2,3-pentane-dione and 2,3-butane-dione or diacetyl extracellular. At the end of fermentation, usually the yeast will clean itself up, but it depends on how healthy the yeast is at the end of fermentation. So these can take in these diones, the vinyl diketones, and convert them to a more flavor neutral diol, 2,3-pentane and 2,3-butane-diol. That's really what you're expecting at the end of fermentation. But all of that goes back to the cell growth at the beginning of fermentation. which is when you have the most production of those intermediates, the alpha-acetolactate. Primarily, the pentanedione is a much lower concentration. Usually the problem is diacetyl 2,3-butanedione and the reduction thereof. To control the VDKs, the residual levels associated with high growth or poor reduction at the end of the process, or most commonly a combination of the two. So if you have a high growth and a poor reduction at the end of fermentation, you're going to have elevated levels of isotyl diketones, of VDKs, of your diacetyl, your butterscotch, butter flavor, buttered popcorn. The elevated production is due to the growth factors, like I said, high oxidation, high temperature fermentation, high trub levels, high fan levels, low pitching rate. So that's a word to the wise, don't underpitch, because you can really have your beer suffer from VDK complications at the end of fermentation if you do so. And then the decreased reduction, typically produced by yeast stress factors, higher alcohols, and perhaps the separation from beer too early. I know that sometimes it's related to bacterial infection as well, so always be careful. I think it's Pediococcus is known to produce more diacetyl than the yeast can reduce at the end of fermentation. So there are other ways for this to happen, but we're talking just about yeast here, not about the bacteria. Then I think this is the last topic we're going to talk about in terms of yeast characteristics, is the POF character. So POF, phenolic character, phenolic off flavor. I personally don't like that it's called phenolic off flavor, because I appreciate that flavor in beer. It's a gene expression. So yeast are categorized into POF positive or POF negative, meaning it's phenolic off flavor positive or phenolic off flavor negative. The POF positive strains have a specific enzyme that decarboxylases phenolic acids like ferulic acid or cinnamic acid and produces those phenolic characters, flavors, 4-vinyl glycol or stearine, respectively, to those two acids. Those, in terms of the flavor, is going to produce clove, spiciness, medicinal flavors. And it's dependent on the concentration, of course. It may give spicy or complexity character to some Belgian ales or wheat beers, like a Hefeweizen or a Saison type yeast or Saison type beer. Typically, you're looking for those phenolic characters, whereas it can be extremely undesirable in other beers, like a Pilsner, or an American light lager or a stout. Although I've heard that one of the big stouts uses a POF positive strain, but usually is an undesirable flavor, which is why it's called phenolic off flavor. POF positive yeast strains and POF negative yeast strains both contain, both of those lineages are in beer yeast. Wild yeast are typically POF positive. Like we were discussing earlier, the fact that most wild yeast are also diastaticus or can be diastaticus, and the relationship between diastaticus yeast strains and being POF positive. But at some point in the selective process, brewers must have selected for the yeast that is POF negative. It's really not easy to find in nature. It's really not easy to find in terms of a wild yeast, a POF negative yeast strain. So it must have been that medieval brewers were selecting the beer and moving forward with the yeast that wasn't expressing that spicy character. And I guess the last point that I would make in this is that, again, I think I appreciate that flavor. We did select yeast strains, WB06, B134, T58, H18 we now know is POF positive as well. We did select those yeast strains on purpose, so it is a positive characteristic of beers. It's just that it's not a positive characteristic for all beers. Here's the actual decarboxylation, and you have ferulic acid on the left side, 4-VG, 4-vinyl glycol on the right side. It's a decarboxylation from the enzyme that's present in those cells, in those yeast, that they're able to convert this. So if the strain is POF negative, it doesn't have that enzyme, therefore it can't convert the ferulic acid to the 4-VG. The ways to control it, you can influence the mashing parameters or even the ingredients used. Wheat being one of the higher grains containing, or the grains containing high ferulic acid. I looked it up, and the grain that I could find that had the most was amaranth, but that's a very small grain, not usually used in beer making. But wheat and rye tend to have more ferulic acid, more of the precursors for 4-VG. So you can control the mashing parameters to avoid the release of the precursors, or you can also modify the recipe so that you're not using grains that have high ferulic acid or high cinnamic acid content. Also, a big one is to avoid contamination, because wild Saccharomyces and non-Saccharomyces yeast are usually POF positive. So be very careful in terms of your yeast handling and how you're applying yeast to your beer. So we went through all of that material leading up to now to get to the baseline. So all of that material was to try to introduce you to the different flavors and aromas that yeast can produce in fermentation. All of them are going to have different characteristics, just naturally, just the intrinsic character of those yeast strains. But Fermentis wanted to take our yeast and to create a visualization, to create something that made it easier for you to understand. So you're not looking at ppm or ppb of different compounds. And so what we did was we set up a series of fermentations. We set up an experiment to test all of our yeast in to see how they compare to one another. So this is what we're going into with the baseline. So what is the Fermentis baseline? We did what we considered to be the most neutral wort that we could produce. So it was a 15 Plato wort, 100% spring 2-row malt, 3 EBC. So really just a very neutral malt, no specialty malts, nothing that's going to really impart too much flavor. In terms of the bitterness, we targeted 25 EBU with just isomerized alpha acid extract, so something like ISO 30, just the bittering compound, the isomerized alpha acid, the bittering compound in beer, so that we had the bitterness, so there was beer flavor, but no hop character. Then we did the pitching rate of 50 grams per hectoliter for all the yeast, regardless of if it was an ale or a lager. We fermented at 23 degrees C for all of the yeast, regardless of if it was an ale or a lager, and it was all fermented at atmospheric pressure. Again, the idea was to create this picture of all of our yeast in the same conditions, in the same media, the same wort, 15 Plato, 25 EBU, same pitching rate, same fermentation temperature, atmospheric pressure, all so that we could say, this is how these look compared to one another. So that was subjected to taste panel. Taste panel came back with their responses on how they appreciated the flavors in these beers. It was all blind tasted. They didn't know what they were tasting. They didn't know what yeast it was. All they did was they received a blank glass. They smelled, they tasted, they rated it on a scale. We took that scale and we converted it to a visualization. So here you see 3 axes. You see fruity, you see spicy, and you see neutral. Down at the lower right corner of this, you see that the neutral with the 3 asterisks is representing raw material expression facilitated. So it's really, the yeast isn't changing the flavor of the raw materials. It's really just fermenting and not imparting a very big flavor if it falls along that neutral axis. The farther out on the fruity axis, the more to the left the strain becomes, the more there was the appreciation of esters or fruitiness in the beer. Likewise, the more to the right the strain is, the more the perception of spiciness, or here what we're saying is that it's mainly phenolic character. So here again, sorry I didn't say this at the beginning, the yellow boxes are the SAF lager, the dark boxes, dark maroon, are SAF ale, and then the kind of pinkish purple color is the yeast and enzyme. And here, what we wanted to do again was to give you a visualization. So you could say, all right, I have this idea for a beer that I want some spiciness to, but also a medium amount of fruitiness. And you can go onto this chart and you can say, here, going up the spiciness, something that I want something kind of spicy, but also something kind of fruity, and you make an intersection of those two lines and you arrive somewhere in this area. Or you say, I want something that's very fruity and not spicy at all, and you just go up the fruity axis and you select up here somewhere. Or I really don't want the yeast to impart that big of a flavor on the beer, so I'm going to come down here where it's just a neutral flavor coming from the yeast. It's not really imposing any fermentation flavors, or I guess the more appropriate way to say it would be it's imparting less fermentation flavor into the media, so I'm more able to appreciate the raw materials that were used. So this is we call it the make your choice diagram. It's really the baseline because this is how the yeast in the fermented portfolio are reacting in a very neutral fermentation environment. So that is the first dimension of the fermentation. Here are the upcoming webinars that are coming soon. June 30th, there's webinar number 2, the second dimension, the influence of fermentation parameters. On July 7th, I'll be back talking about the third dimension, the interaction with raw materials. And then the last frontier, the production of hard seltzers, is with the other regional sales manager of North America, Jose Pizarro, who is not one of the people on the webinar today. And then beyond the 14th, there will be more to come for sure. So with that, I thank you for your attention. I welcome back Anne and Brian to come help me with the questions that have come up or may come up. And thank you.
Okay, you hear me, Kevin?
I can, yeah.
Okay.
I'm not, am I online?
I hear you.
Yep.
Okay. I think you hear me, but you don't see me move. All right. I think we had a few questions during the webinars, but we answered them. So if there are more questions, maybe feel free to type them now. Stefan is typing.
It's a long question.
It's always suspenseful. What are we gonna get?
Stefan says, thank you, Kevin. Very well presented. That's a good comment.
Thank you. Yes, I did have to hold back a little bit just because of the timing. I mean, I went close to, I don't know, an hour and 20 minutes or an hour and 15 minutes. So I was trying to move through the information quickly so that we could get to questions if there were some. But I appreciate the comment. Thank you.
All right, whatever.
Thank you.
Okay, Ryan is asking more about needing or not needing oxygen before pitching. not being needed. Can you go back to the need of oxygenation, Kevin?
So the oxygen is when it comes to the fermentous yeast coming from the dry package, the yeasts have already enough sterol and unsaturated fatty acid that they don't require any oxygen for the first fermentation. Usually, I think the statement is that the yeast can multiply tenfold without any oxygen demand. And in a typical fermentation, you'll have 2.5, 3 times splitting. So you end up with 8-fold growth. So you're within that 10-fold growth. So the yeast, in fact, don't need oxygen for that first fermentation. Of course, you can add oxygen. The yeast are still going to assimilate the oxygen, but it's not necessary for that first fermentation. If you do decide to repitch, then of course you'll need oxygen. If it's not coming from the dry package, then we would recommend that you oxygenate the wort. But if you're using the yeast directly from our packaging within our quality standards of the package being sealed, you do not need to have dissolved oxygen in your wort.
All right, perfect. Actually, we have a question from Clément. Clément is asking about easy to use. I know we had a webinar a few weeks ago concerning this. Brian was giving the webinar, so maybe you can answer the question, Brian. Clément would like to know if there is a need for rehydration and what would be the difference in fermentation if you do rehydrate versus not. Would there be a cell count difference or not?
Sure. So we conducted a study to look at the various methods of rehydration, looking at what types of media are the best to rehydrate in, what is the best procedure, and then also looking at whether it's okay to direct pitch dry yeast into a fermenter. So we created a whole study. You've probably heard of people say that you can't rehydrate yeast in distilled water. You shouldn't rehydrate dry yeast in wort. And we wanted to investigate this and be able to tell brewers what is the best. And what we discovered is that we looked at 3 different types of water: distilled water, tap water, mineral water, and found virtually no difference in the viability following rehydration. Regardless of the type of water, the tap water would have been from Ghent, Belgium, and would have had a small amount of like chlorine sanitizer in it. But the 3 types of water made no difference. And then wort of 7, 15, and 25 Plato, I believe, or 7, 14, and 25 Plato. Can't remember off the top of my head. And again, saw virtually no difference in the viability or fermentation performance following rehydration using different densities of wort. And then we went on again to evaluate conducting a separate rehydration step versus just directly pitching dry yeast into the fermenter. And again, found virtually no difference in fermentative performance or the resulting flavors of beer. So I guess it's kind of a trick question. Yes, yeast needs to be rehydrated, but it can happen directly into the wort, into your fermenter. Hopefully that answered the question. I kind of rambled there a little bit.
All right, Clément, did we answer your question? Yes, we did. Great. Thank you, Brian.
Mind blown.
Yes, exactly, Clément. No headaches needed then.
Yeah.
Easy to use. Great.
Yeah. I think one of the reasons we did that whole rehydration study is that for years and years, Fermentis recommended a rehydration step. It involves adding the dry yeast directly to the rehydration medium, and then a series of wait times, and then gently stirring the yeast, and then adding it to the fermenter. But we heard so many brewers saying that we just direct pitch into the fermenter, so we wanted to be able to validate that practice. And what we found out is that it's perfectly okay to do that. So what we did find is that agitation can have a negative effect on the yeast. So, yeah. Throwing my giant flasks away.
I mean, the conclusion to that study is that you don't need to rehydrate. You can if you still want to.
Yeah.
We just didn't see any advantage in doing so. Yeah. I would say that the one difference that you could maybe assume is maybe like you would avoid the time that the yeast would take to rehydrate in the fermenter. So you would have 15 to 30 minutes faster of a start to a fermentation, but when you're considering a 7 to 14, 21 day fermentation, depending on what temperature you're at, is 15 or 30 minutes going to really do anything? And in that way, I think, no.
Yep.
Chris is asking, how many generation of yeast have you found can be used before yeast health begins to decline with average gravity? So Chris, I assume your question is how many times is our recommendation for repitching? Yes.
Yep.
You want me to answer that?
Sure, I'm the moderator.
All right, so in terms of the Fermentis perception, we say somewhere between 4 and 6 generations, depending on your ability to handle the yeast and to collect it sterile or as sterile as possible. But I can say it truly is strain dependent as well. I mean, that's something that we didn't cover in terms of these characteristics, but some strains are more accepting of serial repitching, and they'll continue to produce a very similar flavor, very similar beer in the same timeline, where others can begin to differentiate themselves from the first pitch quickly. So we would say 4 to 6 generations to be safe. However many times you decide to do that is really a decision that you make. We can't stop you from going more than 6. We just say that to be safe, 4 to 6 generations is generally a comfort zone. With USO5, I say 4, maybe up to 6, just because of when we were looking at the kinetics. USO5 does have that lag at the start of fermentation, and anytime that you have a lag phase, there's potential for a different microorganism, whether you intend it to be there or not, for a different microorganism to really dig its feet in and start to grow and start to populate the media. So with USO5 having that lag phase and that elongated fermentation, there's more susceptibility to some problem in the process. So I would personally recommend 4 up to 6 at the most generations for USO5.
All right, we have more questions. Okay, great presentation. Thank you. Love USO5, by the way. Great. It's nice because half of the comments are question and half are just nice comments. It's really nice to be here with you guys.
It's a very.
I appreciate the comments. It's much easier for me if I don't have to answer questions.
All right. Anyone else? A question? Just
Last call.
Could be a general question. We hope to see you at the next webinar. So the next one is exactly in a week from now.
Good. Great.
All right. Thank you, Clément. Thank you, Ryan. Thank you, everyone. Thank you,
Yep.
Kevin.
Yeah, thank you.
Call it.
Thank you.
Thanks, everybody.
And you will receive an email in I think it's approximately in an hour. So you'll be able to, there is a link to download the presentation.
It'll be a link at the bottom of an email, I believe. So.
All right. Well, have a good rest of your day, everyone, and see you soon.
Thanks, everybody.
Bye.